Hey guys, let's do a quick revision on Redox. Now, Redox is not a difficult chapter on its own. It's very simple to understand, but the issue with the chapter is not the content of it, but how it's structured or how it's presented to you. Now, understand that you're studying chemistry like this. The smart way, I guess, the logical way, right? Now, you first start with atomic structures and you go all the way down to electrons, bonding, then you understand a bit of redox and metals. And that's where the problem lies because redox is essentially kind of came way before our understanding of atoms and electrons. So, how science works is that back in the day, like 2000 years ago, people didn't know science, they just did things and it worked. For example, you could take iron ore, react it with carbon, and it would form pure iron with a lot of carbon dioxide. Not going to bother balancing this out currently, right? You could produce iron that way. Now, this process didn't have a name. They didn't understand what this was. You call this, you have a very good understanding of what's going on over here, right? They didn't. They saw an iron ore. People 2000 years ago, they weren't scientists, right? They were just smiths, blacksmiths who work on metal. So they saw iron ore turning into iron, and they thought this weird magical process took rock, this reddish rock, hematite. They didn't even know what it was called. They just thought it was a red rock, and if you found the correct red rock, and if you heat it with carbon, it's gonna produce this shiny little metal inside which you can use to make swords and pots and pans, right? But one thing they noticed was the iron ore was much heavier and the amount of iron you got was very little because this is a compound and you're getting extracting just pure iron from it. So the mass was reduced. So they call this process reduction. Now the name stuck, right? The name, what it's called, this stuck. And we have weird names for the entire process, right? And in our understanding, but these names are kind of like we have to kind of go with, right? Now, so just to reiterate, this was how science progressed. They knew about metals 2000 years ago, even before that, right? And they didn't know about redox, but they just started, they didn't understand it, they just had their own idea of it. I think it was just primarily magic, that's what they thought. And this is roughly how they kind of progressed. So the old words are kind of still here, so that's where the word reduction and oxidation comes from, and it's just there, right? So that's one major confusion of the entire redox process. What exactly is going on? So you gotta be aware that why is it called reduction or oxidation? Where they're coming from, and why is this important to us? If you understand this, redox becomes much more, you're more accepting towards the whole redox chapter rather than crying about like, oh well, what's redox, right? So let's begin. Here are some words. Now, if something is called a filter, what do you think it does, right? So the name comes from the action it does, right? So it's a filter, a terminator would terminate things, right? An eraser would erase, so you know what it is. A controller controls, right? A remote controller or an AC controller, right? So these are words coming from what they're doing, what action they're doing. Uh, don't think about reduction, reduction, and oxidation like that. Reduction and oxidation like that. Now, reduction has very little to do. Now, the origin of the word is kind of where the word comes from, right? Like how they started thinking about it in the previous slide. I kind of hinted on it, but think of these as Arabic words or something, it means nothing related to the word to be reduced or the word to be oxidized. Well, oxidized comes from this, or like anything to do with oxygen. Just don't think of it like that. It's not reduce, it's not oxidation. You gotta think about these words like, oh, there's some German words or some Arabic words, and it's a coincidence they sound similar to English. I was earlier thinking this might mean something is reduced and some size or electrons or something is reduced, but that's not the case. It's not where the word comes from, right? And same over here. Stop thinking that it has anything to do with oxygen. These are complete alien words from an alien planet, right? Just don't stop thinking. Once you do that, just pretend it's like, just delete the word reduced and oxidation from your mind, right? And from the next slide, we'll give it new meaning. Now, all of chemistry is just about exchange of electrons, right? Now you can gain electrons, you can lose electrons, and we've already seen this in ionic compounds and covalent compounds, right? Now, let me kind of draw a parallel with another chapter, another subject in O levels. Let's go, well, that's physics. Now in physics, what you've done is you've seen a problem about a ball and you see it through many different eyes, and there are many different ways of predicting what's happening to the ball. You can talk about kinematics, you can talk about kinematics, you can talk about you can talk about kinetics, you can talk about momentum, you can talk about the energy, right? Gravitational potential energy or elastic potential energy, convert it into kinetic energy, and it keeps on going. Like, you'll realize sometimes there might be, now you're so good at it, you can always pick the right method to solve a particular problem, but you can also realize, I can also figure it out the other way, right? Like, you can probably use change of energies to figure out most problems if they're going up or downhill, but you can also use your simple Newtonian mechanics to figure it out. So there are many ways of looking at the same problem, right? And this is what we're doing. We saw exchange of electrons in terms of ionic and covalent bonding and everything, but we want to also have a twist on it so we can see it other ways, how pragmatic, a more pragmatic way. Pragmatic means a more practical way. And this is why the chapter Redox exists. The only sad thing is we don't do anything too practical to appreciate it. Okay, so our new definition of the gain of electrons is called reduction. The process of gaining electrons, if something gains electrons, it is reduced or reduction has taken place. And we'll call oxidation the process of losing electrons. So gain of electrons and loss. Essentially same thing we've done earlier, but we're gonna now give it new names. Gain of electrons and loss of electrons. Now again, these words are Arabic and from a different planet, right? They're Arabic from a different planet. So they don't mean reduce or anything to do with oxygen. They're just words. You don't know what they mean because they're just coincidentally identical to English vocabulary, but they don't mean anything. The only thing they do mean is gain of electrons, or oxidation is the loss of electrons. And if you have difficulty remembering that, there's always that mnemonic, because I still use it today because I'm terrible at remembering things. So this is it. We're looking at the same issues, the same problems we've done earlier with the new lens, kind of how we do it in physics, and we're calling it oxidation and reduction, which is just the gain or loss of electrons. Nothing new so far. We've just given it new names. Here is magnesium reacting with oxygen to form magnesium oxide. And to balance it out, I'll put a half over here, right? So what's happening to magnesium is it is in elemental form, so it has a equal number of protons and electrons. So it has like a default set of electrons, whatever it comes with in its new packaging, right? So there's no, so you kind of give it a oxidation state when it's matching, the electrons are matching its protons. You call it 0. You can, give it its actual number of electrons, but it just, you'll soon realize this makes life easier. So it's a pure atom when the oxidation state is 0. And the oxidation state is more or less very similar to the charge something has, right? Now, over here, the oxidation state is going to be +2. Why? Because the charge on magnesium, because it is ionically bonded, is +2, because it gives out 2 electrons. Now, oxygen over here has a charge of 0 because it's in its elemental form. So it won't fight with itself to gain or lose a charge. So it's more or less 0. And over here, it has an oxidation number of -2, right? So because it gained 2 electrons. So you got to talk about how, now with our previous definition, you can say that this has lost electrons. This is oxidation. Whereas oxygen has kind of gained electrons because it has a more negative charge now. So you can call that reduction. How do I know? Because oil rig. Simple as that. So when I say reduction, I just mean, oh, it gained electrons, and if something lost electrons, that's just oxidation. Let's say anything reacts with oxygen and forms any oxide, right? And it could be whatever, it could be anything, right? It could be X2O2 or it could be X2O3, could be anything. Now, the act of something reacting with the oxygen and being a part of it, one thing you can be damn sure of is that oxidation will always itself be reduced because it really wants to gain electrons. So oxygen will always be reduced because it wants to gain electrons. Sorry, the charge is not actually -2 here, it's actually -2 here. So it's 0 here, and it's -2 for this oxygen. So whatever reacts with it, it's going to steal its electrons. So whatever reacts with oxygen itself is what? Oxidized. Sheer coincidence that reacting with oxygen is also called oxidized, but it has nothing to do with oxygen. If anything else would steal X's electrons, you would say, oh, X was oxidized by that something else. Whatever is over, it's sheer coincidence. But oxygen, coincidentally, is also a very good oxidizing agent, or like it wants to oxidize anything it reacts with. Why? Because it's a chore. It wants to steal electrons from anything and have that -2 charge per its ion, right? Per atom. So chor ka bacha hai, right? So it's a good oxidizing agent. So a good way of not keeping track of electrons, and if you see anything reacting with oxygen, you can, be dead sure that it will oxidize. If anything reacts with oxygen, it'll be oxidized. Oxidized. Now you don't have to know this, it just helps you a lot when it comes to MCQs and stuff. Anything reacting with oxygen will itself be oxidized because oxygen has nothing to do with the word oxygen. Ye bas chor ka bacha hai, like I said, right? So in other words, oxidation can be loss of electrons, or another definition of oxidation we can come up with is reacting with oxygen, right? Because every time you react with oxygen, you lose electrons anyway. So anything reacting with oxygen is automatically, inherently, indubitably oxidation. So oxygen, you just from oil rig, is considered loss of electrons But anything reacting with oxygen is automatically losing electrons, so you can also call it gain of oxygen. And when you see a gain of oxygen, it's also oxidation, right? Now on the other side, reduction is actually gain of electrons. And you can make the reverse statement. If loss of electrons is oxidation and reduction is the opposite of oxidation, so it is gain of electrons, this should also be true. Reduction is also the loss of oxygen, right? The reverse is also true. And you can make a chemical equation where you see oxygen being lost from something, and you can check, you can tally the electrons, and you'll realize it's also gaining electrons when it loses oxygen, right? Check out MgO turning into back to magnesium and oxygen. Magnesium oxide is reduced. Or iron oxide, the more famous example, reacting with carbon, iron oxide is reduced to iron because it lacks, each iron ion lacks 3 electrons, and when it turns into an atom, it gains those 3 electrons from the oxygen and is hence reduced. One example we'll not talk about, but it's also there and kind of helps, is that loss of hydrogen. Same principle applies. Loss of hydrogen is also considered oxidation, whereas gain of hydrogen is considered reduction. And that's true because it's the exact opposite of oxygen. Oxygen, when it reacts, gains 2 electrons. Hydrogen, when it reacts, it likes to give away its electron and turn into a plus ion. So anything with reacting with hydrogen, anything that gains hydrogen also gains an electron. So gain of electron becomes reduction. All right, I hope you guys understood oxidation and reduction, what they are, and how you can quickly identify them through loss of oxidation, loss or gain of oxygen, or loss or gain of hydrogen, or even loss or gain of electrons if you can keep track of those, right? So far, it's just that. Know that oxidation and reduction are just gain and loss of electrons, right? Now, here's one thing. Here's where you have to kind of do some math. Let's say this is a new thing, right? Now, let's say you have copper oxide and you want to figure out what is the charge of copper over here. It is not in its atomic form. It has some charge because it's ionically bonded, right? What is the charge over here? How do I figure it out? Well, there's certain rules and you can apply some math to it and figure it out very easily. The entire compound, the first rule is the entire compound has a charge set to 0. So whatever the individual charges are, or the individual oxidation states are, the net charge on it is 0. And that kind of makes sense because copper coming from reacting from oxygen, copper doesn't have a charge, and when it reacts with oxygen, it doesn't have a charge. So it's 0, 0. So whatever the product is should also have a 0 oxidation state, correct? And that's the idea. So any compound, anything that's not an ion, will always have an oxidation state of 0. Now, oxygen, we can know from history, is that will always, when it reacts, always gains 2 electrons, right? So the sum of these charges are because of the oxygen present and the copper ion present, right? And we don't know the charge on this, right? So oxygen, like I said, will always be -2. So I'll put a -2 over here. And this equals to 0. Plus the copper ion, which I don't know the charge of. So I'll just put an X over here. And when I do math right now, I figure out that this is +2. Right? So the charge on copper, the math is telling me the charge on copper is actually +2, or 2 plus the charge, but the oxidation number is +2. You just change the sign where it's written. If it's a charge, the sign is over here, and if it's an oxidation number, it's over here. But it means the same thing, right? So this is how you can do some math and figure out unknown charges, and this is useful to identify oxidation and reduction. I'll tell you how we can do that right now. With the same example, copper can react with oxygen, right, to form copper oxide. So you don't know the charge of copper. You don't know the charge of copper over here. Sorry, you do know the charge of copper over here. It's 0 because it's in its elemental form, right? Now, obviously you can see copper is oxidizing, but what if it wasn't oxygen over here? Or what if it was something else and you had to figure it out? You just knew what was happening to this element. So you do the same process and you'd figure out that the charge over here is +2 and it starts from being 0. So this is considered loss of electrons because the charge is increasing positively. Electrons are negative, so that means electrons are decreasing. So that's loss of electrons. So this has to be oxidation. Oxidation. Here's another example. With respect to carbon, can I figure out what the carbon's oxidation state is before and after the reaction, and if it has oxidized or reduced? Now, some of the smarter people can go just like, oh, it's reacting with oxygen, so it has to be oxidation, and you're not wrong. But we're just practicing, so we'll just do this example and figure it out the other way, because it's not every time you'll see a compound react with oxygen. So we're just practicing with easier examples, then we'll move on to more harder examples. Okay, so the oxidation number, it's not a pure element. The oxidation number of carbon is unknown, and there are 4 hydrogens bonded to it, and the sum of the entire all sets of charges on this methane or molecule is equal to 0, right? Now carbon still being X is our unknown, and 4 of hydrogen. Now hydrogen can only lose 1 electron, so it forms a oxidation number of +1, plus 1 charge, and that is still equal to 0, and I can figure out that the carbon has an oxidation state of -4. So over here carbon is -4. Can you guys pause and figure it out for carbon dioxide? All right, for carbon dioxide you have 1 carbon, which is my unknown, and it's not the same as the old one, right? And you have 2 oxygens like that. It's not a 0, that's oxygen. It's O, that's a 0, right? And each oxygen will always have a charge of -2, equal to 0. So X equals to +4. So it gained 4 electrons. So from -4, it went to +4, so a gain of 8 electrons. So to speak. And that's called oxidation, because gain of, sorry, oh, it lost electrons, sorry, because it had an abundance of 4. Now it's in debt of 4 electrons, so it lost 8 electrons. So that's oxidation. Oxidation, and that's the idea. All right, so certain things you need to know to figure out oxidation numbers of unknown elements, like how we did it for carbon, right, is that group 1 elements, whenever they're bonded, will always have a oxidation state of +1. Group 2 will always have an oxidation of +2, and group 3 will always have a oxidation of +3, right? Chlorine is always -1, and oxygen is nearly always -2, but sometimes you'll see 1 or 2 exceptions, but hardly, right? They won't quiz you on it, they won't ask you to remember it, but know that if this molecule is there and you try to figure out the oxidation number of it, you'll have a hard time because it doesn't behave how it normally does, right? So more or less just ignore this. It's probably more important for A levels, so just ignore this point. One thing we can add here is know that hydrogen, with a few exceptions, hydrogen will always make a +1 charge, right? So its oxidation state when bonded to anything will always be plus 1, right? And only transition elements can have variable oxidation states. That means just more than one variable oxidation states, meaning they could have more than one charge. Case in point, you have iron 2 plus and iron 3 plus. Oxygen won't have that, rarely have it, right? Hydrogen can't, and group 1, 2, 3 elements will not. They'll always be stuck to their group numbers. And that's practically it for oxidation and reduction. And if you think this is a lot, just try writing this down in notes and you'll realize this is not more than 5 lines, right? Most of the lecture went on me trying to tell you that forget about reduction and oxidation being words and just think of them as alien words. I hope this helps you guys, and let's try doing a lot of redox related questions. So which equation represents a redox reaction? Now, a redox reaction is where oxidation and reduction are taking place at the same time. So if A reacts with B to form C, or like AB, fine, let's go with that. If, let's say, A has been oxidized, B has to be reduced. Why do I say that? Does that make sense to you? Oxygen is loss of electrons, right? This is loss of electrons. A underwent a reaction and its electrons were stolen from him. So someone had to steal those electrons or gain those electrons. So it has to go somewhere. So somewhere, maybe B, or maybe if this was a huge equation, someone else had to gain those electrons. So as soon as you see oxidation or loss of electrons, know that somewhere else reduction is also taking place. So oxidation and reduction go hand in hand. There's no just oxidation or just reduction, unless you're talking about electrolysis where ions go to a certain place and either oxidize or reduce, right? So with that said, silver ion reacts with chlorine ion to form silver chloride. It's ionic. So ionic compound which still has the same charge. So the charge exchange hasn't really happened. They're just joined together. There has been no exchange of electrons because this is an ionic compound and they were ionic to begin with. If they were metals, different reaction. If there were metal and gas, this would have been a redox reaction. But right now, silver ion is still a silver ion and chloride ion is still a chloride ion. At most, this is a state change at best. It probably is a state change. This is probably going from, if you had to see this in real life, this is going from an ionic plasma, because it's superheated in ionic form, to a solid. All right, same case with B. Ions, ions. H plus and OH, that's the charge on it, and they're forming together. It's not really an ionic compound, but same thing, more or less. Nothing is really happening here, right? There's nothing really going on. Okay, last one, if you take a look what's happening to zinc. Zinc has a charge of 0, and now it's plus 2. It lost electrons. It oxidized. So somewhere in the world, those electrons had to go somewhere, and copper is balancing it out. Definitely, it's being reduced. So if you're smart enough, and if you're confident you've identified the oxidation correctly, you know the entire reaction is oxidation. Copper indeed is being reduced because it's gaining electrons. 2 plus turning into copper metal. All right, the equation shows a redox reaction between iron chloride and chlorine gas. The equation which equation describes the reduction process in this reaction? So if you just focus on, there are two elements over here. There's iron and chlorine, and over here, right? So let's see what's happening to iron. what's happening to iron is iron, just iron. If we have to ignore the chlorine over here, what's the charge on iron? It's 2 plus currently, and it's turning into iron 3 plus, right? Now, so it's losing an electron to form iron 3 plus, and it's undergoing oxidation. Right? Now take a look at chlorine. Something interesting is happening to chlorine. Something very unique and very interesting. The special thing over here for chlorine is that there are two chlorines. This chlorine has a charge of -1 each. It's in ionic form, right? It's bonded with iron. This chlorine, on the other hand, has a charge of 0, right? So let's call this chlorine A, and let's call this chlorine B. Let's talk about chlorine A. Now note that both chlorines, whatever they do, they're forming chlorine -1 again, right? So speaking of chlorine A has a negative charge and is reacting, and this is still chlorine A. This is chlorine A and B combined, so they're essentially the same, right? They're turning into the same thing. So chlorine over here also has a negative charge, so this is chlorine. So nothing is really happening to this chlorine. Chlorine A, there's no reaction going on essentially, redox wise, or gain of electron or loss of electron wise. Then you have chlorine B, which is Cl2, so it's, you know, in its elemental form, and it's turning into what? Again, this chlorine. Both are turning into this chlorine, both chlorine A and chlorine B. Over here, it has a charge of -1. So it went from a charge of 0 and it gained electrons, so I should write +2 electrons to form 2 chloride ions. So it's being reduced because it's gaining electrons. Okay, which equation describes the reduction process? So this equation should describe it. That's what's happening to this chlorine. This chlorine is the only chlorine being reduced. And iron. This chlorine is actually more or less a spectator ion. You can eliminate it from this equation if you want to. Okay. Okay, so the best answer what we have is B, because it matches B coincidentally. Look at that. The correct answer is B. Potassium magnate, potassium magnate. We didn't talk about this, but I'm sure people know, is a really good oxidizing agent. It's an oxidizing agent. Meaning an oxidizing agent is something that will oxidize anything it touches. So it's gonna oxidize anything it touches. So it's gonna make it lose electrons. It's gonna make it lose electrons. How does it do it? By stealing their electrons. It takes away the electrons, it steals it, and hence gaining it. So the poetic irony of redox is that an oxidizing agent itself reduces. And it's not irony, like think about it this way. A robber will make other people poor if he steals money, because there will be a loss of money, and if that takes place, there will be a gain of money. So if something makes something lose electrons, the currency of the atomic world, it will itself have to gain electrons and be hence labeled a robber, or it's being reduced, or an oxidizing agent, because it's oxidizing something. Okay. When it is added to aqueous solution of compound X, the color of the test reagent changes from, so it has a distinct color when it's in pure form, it's purple, and it goes colorless when it reacts. So, okay, so it's gonna go from purple to colorless and it shows that it has oxidized whatever it touched, so it itself has reduced. The substance X, oh sorry, they're talking about X, not potassium magnate. What? When it is added to aqueous solution of compound X. X is oxidized, of course. I was thinking about potassium magnate. Potassium magnate over here is reduced because it oxidized the unknown compound X. Correct answer is C. In which reaction is nitric acid acting as an oxidizing agent? So there are two ways of figuring it out. Either identify the oxidizing agent, which is nitric acid. How do you identify that? An oxidizing agent will be itself reduced. And an oxidizing agent will oxidize others, right? So I can either look for something else it reacts with and that's oxidized, and if it's hard for me to figure it out, I can figure out that where it's reacting and is being reduced itself, right? So if I'm looking at A, I think it's pretty clear that A, the copper over here has a zero charge. Oops, the zero charge, and now it's ionically bonded, so it has a +2 oxidation state or 2 plus charge. So it has been oxidized. So over here it's only reacting to nitric acid, so A is where nitric acid is acting as an oxidizing agent, right? And it's easy, I'm only focusing on this part. This part, and I see on the other side I'm looking at copper over here and copper over here. The entire equation is too much for me to process. I'm just focusing on these two and the equation on the left hand side. So I'm very sure this is acting as an oxidizing agent. Over here, copper is already in ionic form, nothing's happening to copper over here, so both are 2 plus, so B is more or less out because the nitric ion is still NO3. Nothing is really changing. Over here NO3 is turning into NO2, so that could help. This is a, yeah, still like, yeah, I don't see any major change going on over here. Sodium, nothing's happening to sodium, so it's fine. Same with the last one, nothing's really changing. Sodium is still in ionic form, so I don't want to get into nitric acid itself. Even the nitrate is the same, right? Nothing is really happening except for A. Correct answer is A. Which equation does not represent a redox reaction? So you have ammonia in A reacting with sulfuric acid, so not too sure. It's kind of hard to process. But take a look at B. Element, C, element, element, turning into not an element and producing an element. Let's get a different color for the second one. Turning into element. So element, so over here definitely an oxygen with an oxidation state of 0 is turning into oxygen of a state of -2. Chlorine is changing its oxidation number, and I didn't see that earlier. I also see now that iodine is also turning into an element. So oxidation reactions, reduction reactions, all of them. So chlorine is changing both. Chlorine, I feel, is being reduced, and iodine is being oxidized because iodine will lose electrons, right? Same with zinc. Zinc metal is reducing, sorry, it's oxidizing, and hydrogen is being, what's the word? H plus reduced. Hydrogen is being reduced. Okay. So by default, it leaves A as the answer. Okay. And let's figure out why it's not a redox reaction, because NH3 is turning into NH4 plus, right? So it's not really reacting with hydrogen. It's just collecting a hydrogen ion. Right? It's collecting a hydrogen ion. So it's not that it's reacting with hydrogen, but it's gaining that hydrogen ion. The difference is ion. So if it was H2 and then it would react, so there would be a change of electrons for the hydrogen, and that change would come from the ammonia. But it's already H plus over here, it's H plus. So it's just literally an ammonia molecule with nothing, right? And a hydrogen comes and starts sitting like that. So because this has a plus charge, the entire thing has a plus charge now. So the correct answer is A. Which statement does not describe a reduction reaction? Electrons are gained during the reaction? Well, rig, right? That's true. Hydrogen is gained. Okay, I'm too confused for this. I'll literally spell out my oil rig, which says oxygen is loss of electrons, where this is gain. But I also know, just by the sheer name of the coincidence of the name, this is also gain of oxygen. So this has to be loss of oxygen. And if this is gain of oxygen, there was another element, hydrogen, right? And that has to be the opposite, because what is life if not balance, right? So hydrogen is gained during reduction. Hydrogen is indeed gained during reduction. I'm just matching it with the table I've memorized. It takes place at the negative electrode during electrolysis. Electrolysis, the negative electrode will have the negative charge, and anything coming to it will gain electrons. So that's still reduction. Oxygen is during gained during reduction. During reduction, oxygen is actually lost. So that's not true. So D is not true. And D would be, ironically, be the correct answer. Which reaction is not a redox reaction? And I see elements turning into compounds. See elements turning into compounds. That's the easiest. Last one, definitely redox, because this is known as a reduction of iron reaction, where iron 3 plus turns into iron. So iron is reduced because the oxidation number is being lowered. Calcium reacting with calcium thermally decomposing. So over here you check out each element. They don't have a charge on them. There's no difference of charge on them. So calcium is still 2 plus, oxygen still will be minus 2, and it all balances itself out. There's no change in numbers for the elements. So A is not a redox reaction. So far, it's easier to identify redox reactions and rule them out rather than confirm that if it's a redox reaction or not. Iron-2 ions react with chlorine. I think this is the same equation we just saw a few slides ago. This first or second question we did, right? Or no, very similar, not the same. Wait a minute. No, actually, it's pretty similar. Aside from the aqueous ions, it's pretty similar. Which statement about this reaction is correct? Chlorine is reduced by iron-2 ions. Chlorine is reduced by... That looks true. Chlorine is reduced, and the only one to do it is... Let's just confirm. Chlorine is here, and erase that. Chlorine has 0, -1, so it itself has reduced because it's gaining electrons. So iron has done it, and iron-2 is doing it. Absolutely, A is correct. Chlorine is the reducing agent. Chlorine is itself being reduced. So reducing agents by default would reduce other things by oxidizing themselves, or the other way around. So chlorine is actually oxidized. Sorry, chlorine has been reduced, so it's acting as an oxidizing agent. So chlorine is the oxidizing agent. Iron 2s are reduced. Okay, we don't need to do this, but Oh well. Iron ions are reduced, iron ions are oxidized. Look at that. Iron is oxidized. Iron ions are the reducing agents. So our correct answer is C. Which change always occurs when a metal atom is oxidized? It becomes positively charged? Yeah, I think you're right. It combines with oxygen. It could be anything, right? It doesn't have to be oxygen for oxidation. It gains electrons. Okay, that's not even chemistry, that's nuclear physics. A is correct. Copper 2 oxide reacts with carbon when heated. Copper 2 being oxide reacted with, so very similar to iron reaction, right? This statement about the reaction is correct. Carbon is the reducing agent, isn't it? It's taking away the oxygen, reverse of, so it is a reducing agent. Copper oxide is oxidized. It's actually reduced because it's losing oxygen, or you could figure out that it has a 2 plus charge here and a 0 charge here, so it's reducing. Oxidation number is going down, so it's actually being reduced, right? That's out. That was already out. Copper 2 oxide is the, oh my god, stop it. Okay, correct answer is B. Many reactions involve oxidation and reduction. Which statement is correct? Acidified manganate ions change color from purple to colorless. Purple to colorless. All reactions that involve oxidation also involve reduction. Yeah, I think that's what I was saying, but let's put a pin over here because we don't exactly know what exactly they're talking about. But it should. I mean, the exception would be electrolysis reactions. But let's put a pin on it. During a reaction, oxidizing agents lose electrons. Oxidizing agents undergo reduction, and reduction is gain. So that's incorrect. Reduction is the loss of hydrogen from a combined. Every time I see this question, oil rig. So we can talk about electrons, oxygen, and hydrogen, and electrons, oxygen, and hydrogen. So in oxidation, that is loss, so that goes down, so that goes up. Oxygen in oxidation goes up, so it should go down here, and this, because it goes up, actually goes down here, and this goes up. So what are they asking for? Reduction is the loss of hydrogen from a compound. It's actually the gain. So they're out as well. So that's what I was saying all the time. But you know, your exception is electrolysis and whatnot. But electrolysis, we're at a cathode or an anode, we're looking at half a reaction. But in the overall reaction, it is indeed redox, right? Electrochemistry, another word for it is redox chemistry, right? Something similar, or redox chemistry. I think that's what they call it in the syllabus for A levels. Which reaction is a redox reaction? Metal to iron, definitely a redox reaction because I see oxidation being taken place. So that's definitely a redox. Okay, I don't see any metals anywhere else or anything pure. So I can easily rule out the three and be confident they're not oxidation or reduction. Why am I confident with A is that a metal reacting with anything and turning into this metal compound will have a different oxidation number, will have some positive number and it starts with 0. So it definitely oxidized. It definitely oxidized. And I'm so confident in that, I'm not even looking at B, C, and D.